In project management, schedule is one of the most important elements because it defines the timeline of the entire project. A schedule tells us what needs to be done by whom and by when. It helps in planning, allocating resources, and tracking progress. Without a clear schedule, projects often face delays, confusion, and cost overruns. A well-structured schedule ensures that all activities are aligned with the project goals and deadlines, giving the team clarity and direction. The planned schedule management process is all about creating clarity on how we will handle the project schedule. It involves documenting the approach and making sure everyone has a common understanding about how the schedule will be planned, managed, and controlled. This includes defining how we will establish the schedule baseline and how we will deal with schedule variances. The key inputs that support this process are the project management plan, project charter, enterprise environmental factors, and organizational process assets. To develop the schedule management plan, we use tools such as expert judgment, data analysis, and meetings. The output of this process is a clear schedule management plan that serves as a guideline for managing time effectively throughout the project. A schedule management plan is part of the project management plan. It defines how schedules will be created, managed, and controlled. It covers methods, tools, baselines, variance thresholds, and reporting needs. For adaptive projects, it also defines release and iteration lengths. Define activities is the process of breaking down the project work into specific tasks that need to be done to produce deliverables. It is part of the planning process group. The main outcome is an activity list, attributes, and milestone list, which help in creating the schedule and tracking progress. Sequencing activities means arranging project tasks in the correct order by defining relationships among them. It ensures we know which activity depends on another and helps build the project schedule. The result is a project schedule network diagram and updated project documents. Precedence diagramming method uses boxes to represent activities and arrows to show dependencies. It helps visualize the sequence of work. There are 4 main relationships: finish to start, where one task must finish before the next begins; start to start, where both tasks can start together; finish to finish, where both must finish together; and start to finish, where one must start before the other can finish. Mandatory dependency, a dependency that must happen in a fixed order, like designing before construction. Sometimes legal or contractual rules make it mandatory. Discretionary dependency. This is a preferred way chosen by the organization. It's not the only way, but the best practice. It can be changed if needed. External dependency. Depends on outside parties, like suppliers, vendors, or government approvals. These are outside project control. Internal dependency. These are within the project and controlled by the team. For example, one task must finish before another starts. The activity list shows all the project activities, while activity attributes provide details like duration, sequence, or required lags. These inputs help in accurate scheduling. The assumption log records assumptions and constraints that may affect the schedule. It helps in identifying risks that could influence activity durations. Resource requirements indicate the skills, quantity, and type of resources needed to complete specific project tasks. The resource breakdown structure breaks down resources into categories and shows how much of each resource type is required, helping in planning and allocation. The Lessons Learned Register captures experiences from past projects. It helps in estimating more accurately by using knowledge from previous similar projects. Project team assignments show who will work on the project, their experience, and their availability. Correct assignments directly impact how realistic the schedule will be. Resource calendars show when specialized resources will be available for project activities. They help ensure that scheduling considers the actual availability of skilled people, making the plan more realistic. The risk register documents all identified risks, including threats and opportunities. By reflecting these risks and estimates, the project schedule becomes more reliable and accounts for uncertainties. Three-point estimating is used to deal with uncertainty in project estimation. Instead of relying on a single number, it takes three different values: the optimistic estimate, the most likely estimate, and the pessimistic estimate. Optimistic means the best-case scenario if everything goes smoothly, most likely represents the realistic or expected outcome, and pessimistic means the worst-case scenario if risks occur. Once we have these three values, we can calculate a final expected estimate using formulas. The first option is the triangular distribution, where we simply average the three values. The second option is the beta distribution, also called PERT, which gives more weight to the most likely value. This approach makes the estimation more reliable and realistic. This slide explains the concept of schedule network analysis, which is a technique used to determine the sequence of project activities based on certain dependencies. There are four key methods highlighted here. 1. Critical path method. This method helps determine the longest path through the project schedule. It identifies critical tasks that directly affect the project's completion date. Any delay in these tasks will delay the overall project. 2. Monte Carlo method. In this method, computer modeling and simulations are used. By feeding input values selected randomly from probability distributions, the model generates a range of possible outcomes for the project schedule. This helps in understanding the likelihood of meeting deadlines under uncertainty. 3. What-if scenario analysis. This technique evaluates different scenarios, such as delays, resource shortages, or changes in scope, and observes their impact on the schedule. It helps in proactive planning and risk assessment. 4. Resource optimization techniques. These techniques ensure the most effective use of resources, balancing workload, and avoiding under- or overutilization. This may include resource leveling or resource smoothing methods. In summary, schedule network analysis combines these methods to create a realistic and reliable project schedule. This slide explains the critical path method (CPM), a core technique in project scheduling. The critical path represents the longest duration path in a network diagram, meaning it shows the minimum time required to complete the entire project. Any delay in critical path activities will directly delay the project completion. Another important concept here is float, also known as slack. Float refers to the amount of time a task can be delayed without affecting the overall project deadline. There are three types of float, and on this slide we see two of them. Total float slack. This is the amount of time an activity can be delayed or extended from its early start date without impacting the project finish date or violating any schedule constraint. Free float. This refers to the amount of time an activity can be delayed without delaying the early start of any succeeding activity or violating a schedule constraint. Understanding float is crucial because it allows project managers to identify flexibility in the schedule and allocate resources effectively. Float, as we discussed earlier, is the amount of time an activity can be delayed without impacting the overall project schedule. The calculation involves three main steps. Identify the critical path of the network. Start by determining the longest path through the network diagram, as this will define the total project duration. Follow the forward pass. Using the forward pass method, calculate the early start and early finish for each activity. This tells us the earliest point an activity can begin and end without delay. Apply the backward pass. Using the backward pass method, calculate the late start and late finish for each activity. This indicates the latest time an activity can begin and end without delaying the project. Finally, the formula for total float is total float equals late start, early start, or late finish, early finish. Total float equals late start, early start, or late finish, early finish. This calculation is essential because it helps project managers understand where there is scheduling flexibility and where tasks are strictly constrained by deadlines. This slide revisits two key scheduling concepts, the forward pass and the backward pass, which are used in calculating activity start and finish times. Forward pass. In this method, we begin from the project start with time 0. We move through the network calculating how early each activity can start and finish. The early start S is the earliest possible time an activity can begin, and the early finish EF is the earliest it can be completed. Forward pass helps us establish the minimum project duration and identify early scheduling possibilities. Backward pass. Here, we move backward from the project's end date. We calculate how late each activity can start and finish without delaying the project. The late finish LF is the latest possible finish date, and the late start LS is the latest possible start date. Backward pass helps us understand the maximum flexibility available in the schedule. By combining forward and backward passes, we calculate float-out slack, which tells us where flexibility exists and which activities are critical to keeping the project on time. This slide demonstrates how to calculate the critical path in a project schedule using a network diagram. Here, we have 5 activities with their respective durations. Activity 1 equals 3 days. Activity 2 equals 3 days. Activity 3 for days. Activity 4 equals 8 days. Activity 5 equals for days. From the diagram, we can see the possible paths from start to end. Start 1, 2, 4, 5 and equals 18 days. Start 1, 3, 5 and equals 11 days. The longest duration path is 18 days, which becomes the critical path. That means any delay in activities 1, 2, 4, or 5 will delay the entire project. Notice that in the diagram, activities 1, 2, 4, and 5 have a float equals 0 because they are on the critical path. Activity 3, however, has some float, meaning it can be delayed without affecting the overall project completion. This example clearly shows how identifying the critical path helps us focus our attention on the most time-sensitive tasks. This slide explains schedule compression, which helps in meeting tight deadlines by reducing project duration without changing the project scope. There are two main techniques: fast tracking. Instead of doing tasks one after the other, we check if some activities can be done in parallel. This reduces the overall project cycle time but may increase risks. Crashing. This means adding more resources to critical path activities to finish them faster. While doing so, we need to balance cost and schedule trade-offs. The aim is to achieve maximum schedule compression with the least additional cost while still maintaining project scope. This slide shows how to decide which activity to crash in order to reduce project time. We are given original duration, crash duration, time savings, and costs for each activity. Activity A, crash cost per day is $1,000. Activity B, crash cost per day is $2,500. Activity C, crash cost per day is $2,000. Activity D, crash cost per day is $3,000. To reduce project time by 1 day, we select the activity with the lowest crash cost per day. That is activity A because it costs the least to crash while saving time. This slide explains the impact of schedule compression techniques on projects. Fast tracking adds risks and increases management time for the project manager. Crashing adds costs and also increases management effort. Reducing scope saves both time and cost but causes customer dissatisfaction. Cutting quality saves costs and resources but increases risks significantly. Resource reallocation, neutral effect. It does not add costs or risks. So, while schedule compression helps in reducing timelines, each technique comes with its own trade-offs. This slide explains Control Schedule, which is part of the Monitoring and Controlling Process Group. Control Schedule means monitoring the project status, updating the schedule, and managing changes to the schedule baseline. Inputs: Project Management Plan, project documents, work performance data, and organizational process assets. Tools and techniques: data analysis, resource optimization, critical path method, leads and lags, schedule compression, and project management information system. Outputs: work performance information, schedule forecasts, change requests, project management plan updates, and project document updates. So, Control Schedule ensures that the project stays on track and adjustments are made whenever required.